This is a video about the type of transformation called a dilation. We will first look at a definition and then we will do a few examples. First of all, remember that a dilation is a transformation that will change the size of the figure. So it will either enlarge or reduce the size of the image. The original figure and its image are always similar. So we've talked about congruent means same shape, same size. Similar means same shape, but not necessarily the same size. If you have a scale factor of 1, then it would be the same size. Anything else, and it would not be. When you're looking at the scale factor, however big the scale factor is will determine whether the image will increase in size or decrease in size. If you have a scale factor that is larger than 1, then your new image will be larger than the original. That's called an enlargement. If your scale factor is smaller than 1 and it needs to be maybe a fraction or a decimal, if your scale factor is smaller than 1, then the new image would be a reduction and it would be smaller than the original size. If you have a negative scale factor, that will actually flip it over your point of dilation, and it would almost act as a reflection as well as a dilation at the same time. All right, first example, draw the image of a quadrilateral after a dilation with a scale factor of 2, then identify the type of dilation. So we have a picture that we're going to start with. In red, we have the points F, G, H, and J. I can tell that one's the original because I have regular letters instead of the apostrophe or the prime symbol. So first column, I'm going to do original coordinate points. And I'm just going to list what those coordinate points are. So F was at 1, 3. G is at 2, 4. H is at 3, 3. And J is at 2, 1. Okay, in the second column, I'm going to calculate the dilation. So I'm going to do x times 2 and y times 2. Okay, so point F would be 1 times 2, 3 times 2, 2 times 2, 4 times 2, 3 times 2, 3 times 2, and finally 2 times 2 and 1 times 2. And then in the final column, I'm going to do the new points. So the first coordinate point at F, 1 times 2 is 2, and 3 times 2 is 6. So point F prime, I'm going to relabel that. F prime should be at 2, 6. And when we check that, we see that it's right there. So that matches up. G prime, based on our calculation, should be at 4, 8. And we see that it is right there. H prime is going to be at 6, 6. We can plot that point or check it right there. And finally, we have J prime at 4, 2. And that is right 4 up 2. So the image that we saw actually matches our calculations for the new points. Study tip that you'll see here, you can always check your answer. So sometimes, well, most of the time, the new image won't be drawn. You'll actually have to sketch that in. So we would have drawn those lines like this. You can always check your answer because if you start at your point or your center of dilation, you'll see these black lines connecting all of your corresponding vertices. If you did all of your calculations correctly, then those lines will all pass through your point of dilation, which is typically going to be the origin if you're doing your calculations this way. Okay, this time we have a rectangle and we're going to dilate it with a scale factor of 3 and then again with a scale factor of 1/2. So I'm going to set this up the same way as before. I'm going to put my original points in my first column. So I have E at 2, -4, F at 2, -1, G at 6, -1, and H at 6, -4. And I know that I'm going to need those same points again, so I'm going to take a moment and copy them. And then that way they'll be ready when we're ready for the second one. All right, the dilation that we're going to do is the scale factor of 3. So we're going to do x times 3 and y times 3, both of our coordinate values. Okay, so point E be 2 times 3 and -4 times 3. Point F is 2 times 3, -1 times 3. Point G, 6 times 3, -1 times 3. And finally, 6 times 3 and -4 times 3. Okay, third column, new points. E prime should appear at 6, -12. F prime is at 6, -3. G prime is at 18, -3. And H prime is at 18, -12. Now, typically we would probably plot these on a graph and make sure answer is reasonable. This question just said find the coordinates of the new image and then identify the type of dilation. So we have all of our new points in the grid, and because we have a scale factor of 3 and 3 is bigger than 1, we know this would be an enlargement. All right, and that didn't quite work out the way I wanted, so try again. All right, and this time we have a scale factor of 1/2. So we will do x times 1/2 and y times 1/2. Okay, so we're going to do 2 times 1/2, -4 times 1/2. 2 times 1/2, -1 times 1/2. 6 times 1/2, -1 times 1/2. And then 6 times 1/2, -4 times 1/2. Okay, and then we can write our new points. We have E prime at 1, -2. F prime is at 1, -1/2. G prime is at 3, -1/2. And H prime is at 3, -2. Okay, we have a scale factor of 1/2, which is less than 1, so this one would be a reduction. So we know that our new image would be smaller than our original. All right, next we have a little bit of logic that we're going to do. So a figure is similar to another figure if you can create the second figure from the first by a sequence of translations, reflections, rotations, and dilations. Hopefully you saw before that a figure is congruent to another figure if you use only translations, reflections, and rotations. So once we include dilations, now we're going to use the word similar because it might not be the same size anymore. So part A is triangle XYZ congruent to triangle JKL, and how can you tell? So we have XYZ right here. I'm going to trace that. And we can do several different things, one of which, if I slide this up 2 places, so slide it the vertical, the y-axis, 2 spots, and then I rotate it, and if I use that point J as my center of rotation, I can rotate it counterclockwise 90 degrees. And because I can use translation and a rotation to get there, then I know it's congruent. You could rotate it first. So we can go back for a second here. So starting just like this, I'm going to rotate it first, and I wanted to rotate it around point X. So imagine holding your pencil there and rotating it, and then sliding it up. So you can do it in either order and you'll still get the same thing. You might even be able to figure out a way to do 2 reflections and then a rotation to get it to that location. Okay, so we would say, yes, triangle XYZ is congruent, and this is the congruent symbol, to triangle JKL because it is possible to use a translation and a reflection to move one to the other. All right, part B is triangle XYZ similar to triangle PQR. So we know that if I leave this red triangle here, we can already get there. Now we just need to see if those two are dilations of each other. So remember from our study tip, we can check that by using lines that intersect back at the origin. So I'm going to start at the origin, and I'm going to connect all of my corresponding vertices. So get that exactly on there. That one works. Okay, here's my next one connecting J and P. And the third one connecting L and R. Just that, just a touch. Okay, so because I have all of those lines that all intersect back at the origin or our point of dilation, that's one of the ways that we can see that triangle PQR is an enlargement of triangle XYZ. So that's one way that we can say yes and an explanation as to why. We can also use our ordered pairs to see what we're multiplying by or what that scale factor is. So if I look at triangle JLK, that one has ordered pairs of 2, 2 at point J. L has an ordered pair of 4, 2, and K has an ordered pair of 2, 6. Okay, and then I'm going to compare that to the second triangle. We'll do it in the same order, so we'll have P, R, Q. So the point P is at 4, 4. R is at 8, 4. And Q is at 4, 12. So now when I look at each one of these pairs of points, I can see that every value in PQR is exactly double or twice as big as JLK. So because I'm multiplying by 2, I have a scale factor of 2. And I've proven 2 different ways that triangle XYZ is similar to triangle PQR. And then to back that up, I could say first I rotated it, then I translated it, then I dilated it. And remember, those are all interchangeable, so you could do those in any order. If you wanted to dilate it first and get another triangle that was down here, it would show up and be about that big right there, going off the grid just a little bit. You could dilate it first, and then you could take this triangle and translate it up. And then if we rotated it around point P, that would work. So just know that all of your transformations, basically they follow the commutative property. You can do them in any order and get from one to the next. There's also more than one way to do it. So I showed 1 or 2. If you can think of more, then that's great as well. All right, that is everything for dilations. Hopefully that helped you understand them and will help you complete the next assignment.